Hello and welcome back to the video lectures where this video we're gonna go into data mining experiments, how our algorithm fitting works, the tuning of these algorithms, and then the evaluation. So essentially what we will do is piecing together the parts that we've discussed up until now into some form of an experiment. This video will mostly be talking about some concepts that are generally applied in research. So it will be less involved with working out particular algorithms, etc. We'll focus on some simple metrics for doing evaluation. Generally, all the parts that we discuss here are quite important to remember as they are the methods basically for research. So essentially, this is applied throughout the course for most of the components. So let's first talk about what types of research we generally see in the data mining area. I think a rough distinction between the types of research that are done are the more fundamental types of research where people try to develop new algorithms or optimize them or find particular simplifications for these algorithms so that they work on bigger sets of data in a faster way, that they might fit faster, or that they can be applied to particular data sets. Then there's research into the data itself. So that is, for example, collecting it, analyzing it, maybe labeling it, showing what types of interesting properties there are in particular data sets. And then the applications of these two, so that's generally the algorithms to data, maybe doing some prediction tasks or baking this type of research into some type of app. But generally, for all these types of research, finally, there needs to be some evaluation of the quality, and this is generally done through evaluating them against a particular dataset with a bunch of metrics. Now, with all these steps, you can imagine that data mining research being conducted on a computer. It's kind of like a closed environment. You know your data, you know your algorithms, etc. If you run the exact same code, it's gonna give you the exact same result, which you would assume makes reproducibility a lot easier, because I can just drop my code and my data to a different researcher and they should be able to reproduce. And because everything is sort of formally evaluated using these metrics, indeed it's quite easy in theory to reproduce. But it also spawns its own problems in the sense that one researcher's system might be generally different in terms of operating system or CPU, etc. Also, the information that I might supply with my paper might not be complete. I might have forgotten a bunch of implementation details. My code might not be super readable. The data that I was working with might be something that I can't just share with everyone. And also the results that I got might not apply to exactly the same type of data, but just collected by someone else. So how do we test for this, or how does the scientific method apply in data mining research? So for this, we'll have to think about what the end game is of data mining research. So what is the highest achievable goal, essentially? I've stated here that making robust observations is important, which means that a set of observations that we make should be invariant to small changes in the data or in the algorithms, and that they generalize to similar settings, so to the same data or slightly different data but with the same task. Say that we obtain a particular classification accuracy with a particular algorithm fitted on particular data. If we change any of these components, only just slightly, we want to have somewhat similar results. We don't want to bomb the classification accuracy just because we're testing on slightly different data or data collected from a different year or something. Now, in order to guarantee this, we have to fairly evaluate our entire pipeline. And by pipeline, I mean all the components within our experiment that are moving parts, essentially. So collection of data, fitting of the algorithms, etc. And by fairly, we mean critically, in a way that we don't oversell our results, in a way so that we don't misrepresent our experiments and our experimental results. And this might be in that we, for example, report higher scores than are actually true because of some errors. It could also be that we pose that we have solved the classification of a particular problem while we have actually made it into something much simpler that isn't actually the classification task that we say it is. And we will come back to that with a small example. In general, it's also important to strive for having interpretable models, which is a sort of a complex concept to really go into concretely. But you want to some extent, be able to explain or at least have some insight into what models are paying attention to in the data. So if, for example, particular features are important somehow, we, as humans working with this, would generally like to have some insight into our data and what makes these patterns interesting. Because apparently we were not able to observe them ourselves somehow, or we might have, but then we'll never know if a model has actually picked up on them if we can't investigate somehow. And also we want our research to be reproducible. So the practices that we have, we want to port them, as I said, onto a different system with different data, different algorithm, and still kind of generally work if it's within the same domain or the same task. Now notice that this is quite similar to, everything that science kind of strives for. All research practices in other fields have generally the same goals. So if you're doing statistical research or experimental studies on humans, you want to be as carefully as possible in accepting a particular hypothesis, right? You want to make sure that the effect that you have interpreted is indeed actually there and is not some artifact of your experimental setup. So if you repeat the experiment, it should have the same results. So why are these things challenging for data mining specifically? Well, as you can guess, we often deal with very lively streams of data that change from over time. They're very noisy. It's not always a very clean-cut data dump that you might have seen up until now in the course. Everything is generally messy. There's no structure. The things that you want to investigate aren't usually immediately evident. You have to extract them somehow. And doing so generates a lot of components in this pipeline that I was talking about, which is the collection of data, the cleaning of the data, the algorithm implementation itself. So if you're not using a library but implemented some kind of classifier yourself, that might be prone to error. These algorithms have hyperparameters that we'll talk about in this lecture that we want to tune. We have a choice of various evaluation scores that kind of capture different things. So we have to also interpret these somehow and choose the correct ones for the task that we're doing. And then finally, even in the interpretation of the results, we could make mistakes. So this whole pipeline of moving parts needs to be checked and conducted all perfectly, in a sense, or at least correctly. Because if one of these elements messes up, because it's this long thing of sequential steps, if you mess up the first one, the end result will also be unreliable. It will not be an actually true result according to what you reported because you missed a particular bug or an error, right? This also makes this type of research quite frustrating, and we'll talk about that a bit later. So first I wanted to look at a use case. This is a very good example of how a particular task that you set up to do can be misleading, not because you intentionally sought to mislead the audience or the reader, but because you didn't pay attention to your data. So the thing that we're going to work with is this 20 newsgroups data set, which, as you can figure out from the title, is a data set of 20 newsgroup categories that have different topics. So we're not just going to select two, which is SCI space and alternative topics atheism. So this is going to be our data set. It's text documents essentially directly scraped from this newsgroups database or website. And so because we have these different categories, I'm going to say that, okay, I'm going to do some type of topic detection, right? I'm going to see if I can distinguish these two topics. Now, I could have done all of them, but I think for the sake of this example, it's nice if I just have two so I can show you a bit more clearly what is happening. But essentially, it's text classification, right? I'm going to assume that based on the contents and the words that are used, some might be unique for a particular category, that I can do topic classification. So this is how I'm going to represent this in my research. I'm going to write an algorithm or fit an algorithm onto this data and then make a model that does classification of topics. So this is just extracting the data right here. So we have our X and our Y. Then we split them. We're going to go into this a bit more in detail later, but essentially what I also said in the previous video, we want to have a big portion of train that we can fit our models on, and then we want to pretend like we have some new data that would be a test set that we then see whatever we did and fitted if that would generalize in a way to unseen data, right? So that's what we do here. There's a training set and a test set, and then also the labels are split, right? So we're two different Y's. Now this X over here is just raw text. So somehow we need to change this into features that are informative for a classifier. In the previous video, we saw TF-IDF and how that can inform what terms are rare or informative for particular document representations. So here we're going to apply this TF-IDF to our data. So this is going to result in a new data representation that is now a TF-IDF representation. And here we're going to take the terms that at least occur in 3 documents. So if they are too rare, we don't want them in our feature space because it's going to blow it up a lot. And probably these terms, because they're so rare, they will also not really generalize, right? So we want to focus on the words that might. And then here we run logistic regression. We fit it onto our training data. And then we have a fitted model. So here comes the evaluation part. Also, don't worry if you don't understand this code. I know that we have gone into it in some detail in the practicals, but obviously this course doesn't assume that you actually know how to interpret this code. It's just for showing you that this is an actual example. I always like to have these realistic examples, because if we just look at imaginary bar plots all day, we're not going to really get good information, right? So on that note, here we apply accuracy score. Now essentially it's a bit obfuscated here, but what we do is that we just check our y hat and our y, and then see how much of y hat we classified correctly based on what we know are the true labels of y. This logistic regression predict part right here generates our y hat. And then because our X test is not transformed yet into this TF-IDF representation, we have this TF-IDF transform here, and then the predict here. So that's also going to give us our y hat. And what this is going to do is that it's going to report the performance on the training set, right? That's the first part right here. So that will be accuracy for the training set, which generally we want to be very high, right? Because if that is low, it means we can't actually learn our task. So given that we have the actual labels, right? This is not some new data or whatever. We actually fitted using these labels because it's our training set. We want this to be, close to 100%. Otherwise, our algorithm is doing something incorrectly. It's not properly fitted on the training data. Might be that the task is very complicated, right? You never know. As I generally like to say, a algorithm that doesn't necessarily perform very well doesn't make it a useless classifier or a useless algorithm. It's just that theoretically you want that score to be high. Now we can see that here this is our accuracy, right? So that's close to 100%. And then we can see here that the drop off from the test set, so this is the test performance, is very low. So we just lose about 3% of performance. That's pretty good, I'd say. Because this is such a high number, it's you might say, well, we need a bit more context here, and you're right. What we generally want to add here, which I didn't for this example, is what we call a baseline. Now, baselines are an important concept because they give us some very low bar performance, essentially. So a popular one for classification is, for example, just taking the majority class, which we can get by investigating our y. And then we can see that we, for example, have this much of class 0 and this much of class 1. So class 1 is the most frequent label in our y. So if we take 1 as a prediction for all our test set, and we assume that this distribution is kind of the same, then we'll probably already have quite a good score, but we didn't learn anything, right? So majority here is y is 1. We predict that for everything, and then we get some performance which will indicate, given that we learned nothing, how much is our performance. Now for regression, we can just take the average value of y, right? That's also the, I guess, in a sense, the most frequent value, or at least one that will be dumb enough, but always kind of average. So we can already get some lower bar predictions going on. So then we will predict the average for all of the y tests, right? For a test set. And so that's what we're missing here. We're missing some context if this is actually good performance and good generalization right here. And this is something that is also discussed in more detail in the practicals. All right, so what we do here is that we essentially just get our logistic regression coefficients. So the weights per feature, essentially. Now you don't have to know what this syntax is right here. Basically, we just get a sorted list where all the terms are matched with the vocabulary, and then we get some weights. Now the regression coefficients for both linear regression and logistic regression will give us some information on how important the feature is. Now the weights can only be interpreted in context of the model, so they're not hard importances. If you fit a different model with different parameters, you're going to get different importances. But they will generally give you some indication of how important a particular feature is, in the sense that how much weight it gives to the final result. Okay, so with linear regression, you can translate it to an actual contribution. In logistic regression, it's often how much it contributes to the decision boundaries. So the ones that are associated with the actual boundaries are usually the words that belong to a particular class. And you can take the inverse and it will be the ones that belong to the other class. Just from kind of looking at these terms, you can probably already figure if this is either from psi space or from atheism. My guess would be space, given velocity and solar. So these look fairly good. It looks like we're actually fitting things that should be there. Now we can already see that we have a bit of, weird terms here. I don't know what this is. It might be referring to some rocket, a spaceship, a satellite, a star. I don't know at this point. I could look it up, but at the point of interpreting these results, I actually don't know. So I'm naively going to go into accepting that this is fine, and then we're going to look at some interpretations of the weights. This is one way to visualize or to interpret our model. So this is this interpretability thing. We can look at the weights, and then, if we would ever have to explain what our model is paying attention to, we can actually just give these words in the weights, right? Now there's more advanced packages that will actually allow you to give a classifier and a pipeline, and it will do local explanations for you. So what Lime does, it's right here, you can look that up. It's a Python package that's on GitHub. It has a bit more information there. I will give a very short intuition in the results on the next slide. But the code here is essentially making our TF-IDF and logistic regression into a pipeline so that it can be applied in one go to our data, and we chuck that into the Lime text explainer, give our class name so that it knows what is up. Then we give it one instance to explain, because this takes quite a bit of work and time. And then we let it explain our classification difference for 5 features. So focus on the 5 most important features in this particular piece of text, because otherwise we're going to have a lot of highlights, etc. And it's going to be less interpretable. Okay, so here we have the results. So as I said, I would explain what Lime kind of does. What it does is that it takes small windows within the text, and for each of these windows, it's going to make a prediction. So it knows what the contribution of these individual terms in these windows are. And the higher the weight in a particular window, the higher the zone essentially is. You can check this further by just deleting one of the terms in a window. So then you know what the contribution for an individual term is in this local part right here. So not in a larger context, but in a local context. This is not something you need to know in detail. It's just for me to show you that you can actually interpret these classifiers that have particular probabilities for particular terms in a nicer way than just looking at these coefficients. So we can see that this is our text, right? So we have the header here, and then the text starts here, which I cut off because my example will actually focus on the header. We can see we have a 76% probability of it being size space, and then a 24% of it being atheism. And now we have our coefficients right here according to Lime. So these are the weights according to Lime, which are all quite low, but still, it does predict it correctly that this is, orbit data. I think we can assume safely that that is space. I haven't checked the label, but I'm pretty sure. Now, what is the problem here? Remember that I said that we're going to do text classification, right? And we were going to do topic classification specifically, which means that if we were given any piece of text, we should be able to predict, given the text itself, right? If we would have a general topic classification system that would, we know the limitations because we only have 20 categories, but any type of text, for good generalization, we should be able to classify in one of these topics, and it should make sense. Now what you can see here is that it spots this edu extension right here of the email and links that to atheism. So apparently many people with a university account post on the atheism board. So it's paying attention to information in the header, and it's the same here. Now we know that this subject line says orbit data, and therefore it kind of cheats and knows that it's a size space. If it wasn't in the body text here, we would be getting it from a header, right? So this is, in a sense, paying too much attention to the metadata, which is the header. And this information we don't always have. If we just have a random text, there's no headers. That's only a thing with these news groups, right? So if you want to classify stuff beyond the news groups, then we can't use this information anymore. So if you would want to generalize, remove the headers. And this is also why it's important to investigate the classification components of your data using these types of packages. It will give you a lot of insight into these weird artifacts that your model picks up on. Okay, so I just made a rough link with the statistics here, just to show you that the objectives are kind of the same. You can read this. I'm not gonna paraphrase this. I think I discussed most of this earlier, so this is just for your own reading pleasure, so feel free to do that now. Okay, so when we conduct experiments, what is the thing that is most important that we really want to focus on? And what is the essential bit of data mining research? Now, before I said that there's this 80-20 rule, right? There's 80% data, 20% models. I'd like to divide it amongst one more category, which is the investigation of your results. Now, you might say, okay, that's part of my models. I don't think it is. A lot of people spend a lot of time tuning their models, etc., and never even bother to look into detail into what kind of effect their model has on the data and what it's picking up on. They just happily report all the metrics and done. So 10% should be investigating your results. And this is not something that's linear. So first I do my data that costs 70% of my time, then 20, then 10. No, it's iteratively. We work on our data, we run some models on it, then we're going to investigate. And usually you're going to see that either the results are super good, and then you immediately have to distrust your results. Your first reflex should be, this doesn't make sense. If your baseline, for example, your majority baseline gives you a 60% performance, and you got like a 90% all of a sudden, you should spend all your time on checking if this is actually a true result. So you go back into your data, you check all your data again, check that everything's clean, check that your labels are nicely in place, you don't have incorrectly labeled instances, manually look at your test data, then see if your models are properly tuned and you're not leaking some information somewhere, or you just happen to have a very easy split of your test data, etc. So mix those up. Then go back and investigate your results again. And if it turns out you find the error and your performance drops to 70%, you now have to make sure that you go back up to a good result again. 70% might be acceptable, but we might want it to be a bit higher, right? So we go back again, clean our data, tune our models even more, check our results again, etc. Okay, so this is, as I said, what makes data mining research quite frustrating, is that you have all the components in place already, but you need to debug and revisit and reiterate whenever you find an error or whenever you're skeptical of your result. Now, to minimize this time that we spend on this and the risk of misinterpreting our results, we need to, from the get-go, make sure that we know that our evaluations are fair and to which extent they generalize. So we need more than one data set, preferably, and we really want to make sure that we carefully analyze our experiments. Okay, so let's talk about generalization for a bit. So what does generalization look like on a surface level? Now, these plots right here are for regression, and they are mean absolute error, which means that higher is worse, right? We have this train and a test set. So we fitted our regression model on the housing data set. That's actually what this plot is. So it's the Boston housing data set. Then we have two regression models here. We have a simple linear regression, and then we have a regression which uses polynomial features or interaction features. Interaction features are generally taking the product of values of individual features. So say that we have features x1 and x2 and x3. So then we have x1, x2, x2, x3, and x1, x3. So we have three new features, and generally what this tells us is how one feature influences the other. Now, because this is a more complex interaction, it is generally very easy to overfit on this. So it will give us some nonlinear relations, and therefore it's easier to fit a model onto this. And we see that because the simple model has a error of about 3.8, and then our polynomial model on the training set has an error of 2. So it's much lower. So if we would only look at the training set, this would be our preferred model, right? But now that we infer on our test set, you can see that this model actually has a bit of a lower error. So it's actually underfit. So it's not taking full advantage of the complexities of the data set. And this one is much more overfit because a very low error and then a very high error on the test set, right? It's over 12. So all these complex interaction features here have caused their model to overfit too much on artifacts in the data. So this is the bias variance trade-off. The models with high bias don't pay attention to these systematicities in the data, and therefore they underfit, which leads to high error on both the training and the test data, or at least higher than, for example, baseline, or that could possibly happen. So what we see with high bias is that of our target values, which would be the middle of this graphic here, we're generally always structurally off. Now, models with a high variance in predictions, which says something about the spread of these predictions, generally do pay a lot of attention on the unique features of our training data, but that means it pays so much attention to these that it doesn't generalize, which means that, again, they are much more spread around the actual target, as you can see in this graphic right here. So high variance in the predictions means a high spread. And this also implies that they do very well in the training data, right? But then, as we saw on the test data, the error goes up a lot. And notice that we test this for the data that we know. So note that we can only evaluate generalization if we have known labels, so the actual values. Okay, so what does this look like in terms of algorithm fit? So we have these underfitting and overfitting things that we talked about. You can see them from these differences in our train and test set. We could see them if we in detail analyze the predictions and how much they're off and which kind of spread they have, right? So if it's very spread or it's systematically off. And then we have our decision boundaries or our fits that we can also assess in our algorithms. So if we have these very complex interaction effects, or decision boundaries, if we would say for classification, but this would be regression. You can see that this so tightly fits our data that it doesn't really, it pays a lot of attention to these individual effects, right? These small variances, as we call them. And this right here would be more of an ideal line. You can see that it kind of follows the trend of the data, right? But it's not overly paying attention to all these small variances right here. And this is what we would call an underfitted line, so it doesn't pay attention to any of these potential outliers. It just fits this kind of straight line right here and goes into a small slope right here. So this would probably mean that this data set is underfit. Now we could imagine that our test data could be all over the place right here. And because we didn't pay attention to these small idiosyncrasies, this leads to a high structural error, right? So the residuals could be very high. So what can cause these errors? They could be in the data, the way that we collected it or sampled it or something, which is generally not easy to fix. We could, but collecting more would be better. But more often they are in the way that we set up our experiments. Now, one of the things that we generally want to tune are these hyperparameters. And the hyperparameters are parts of the model. So coefficients could be a parameter where the model tunes the parameters itself, right? We don't have to worry about that. Now, the hyperparameters are generally things that we can set ourselves, and we have to kind of fiddle around with to get a better result. So one of the hyperparameters of K and N, for example, is K, so the amount of neighbors that we look at. For decision trees, we can look at decreasing or increasing the depth of the tree, so how many levels we have, and the pruning factor, so that's how much we cut off or try to kind of simplify. If certain rules don't capture a lot of instances, we might want to prune them. And with the regression, these polynomial features, you could say they're part of the data representation, but they do form parts of the regression model, and we can turn them on or off. So we could consider them as hyperparameters. Now, hyperparameters might also be in the cleaning, right? So do we, for example, working with text, do we make everything lowercase? Do we strip off periods and commas, etc.? We could say that that is a hyperparameter of a cleaning process. We could turn that on. Then we have a model that is trained on data where that is in our features, or we could turn it off and then it's not in our features, right? So throughout this whole pipeline, we have different hyperparameters that we can tune. And tuning just means exploring different values or combinations of these values and seeing which one yields the best overall result, which we usually call validation. And we want a different data set for validation. Now, why that is because we have our full data. And up until now, we have only discussed splitting this into train and test. Now, if we would tune our parameters based on the train set performance, again, we will get a very high result because we focus even more on these artifacts in our data. We could get 100% train, and then we only know that that parameter setting works well for train. And then usually when we evaluate it on test, we have a very overfit model due to this hyperparameter tuning. Now, if we would fit it onto our test set, so say we fit different parameter settings on our training set, so we do fit on the train, but then we evaluate on the test set to choose what the best parameter is, right? So we could evaluate case 3 and case 5. We fit those on the training set, and then we test which of these is best on the test set. And we see that K is 5 was our best case setting. We again, we only know that this is good for the test set. So we make a choice based on the test set. And then we don't know how it generalizes anymore. Because we made a choice ourselves, the test set is compromised in a sense. It is not unseen data anymore because we know what the best parameter setting is for the test data. So we do not want to use our test set. We want to leave our test set for the last evaluation after we have made all our choices, everything is set in stone. Only then do we want to get our test set out of our locker and see what the final generalization performance is, or have some indication of this, right? So we need a different set, and the way that we usually do that is that we split our data into 3 splits if we're tuning. So that will be train and a validation set, and then a test set. So what we do is we fit all our models and different hyperparameter settings, etc. on the train. Then we evaluate and choose the best of these combinations on the validation set. So we don't fit on validation. We just test on validation or choose the best parameter setting. And then once we have our winning candidate, only then do we evaluate on test. Okay? So that's important. Now I will go into a bit more detail on this for a bit longer in the next video. But for now, let's also focus on data imbalance. So what could be the case is that we have very large class differences. So the majority class, for example, is 90% of the data set. Now you can imagine if we would split off our test set, and our test set is just randomly split, and it only has, it would be a big coincidence. It could be that we have 10% of the majority class, and then 90% of the minority class in our full data set in our test split. Right, so it misrepresents this data distribution that we have. Now we could similarly look at the values or the feature values or whatever, but usually we just look at the frequencies. So if this is our data set in terms of labels, and this is 0 and this is 1, then we would want our test set to have these bits, right? So 10% of 0 and 10% of 1. Okay, and this is called stratification. So taking a fair sample based on the labels and their distribution. Now we can also adjust the sample. So you can imagine it's very difficult to focus on whatever makes the minority class unique if we have very few instances. What we also could do is just take a different sample. If we have collected the data ourselves, we can always check if we can collect more data that is more fairly balanced. But usually this is not an option, so we will have to synthetically adjust our samples, and we'll go into that a bit further on. So let's first focus on how do we actually choose good hyperparameter settings. So as I told you, we split off a validation set. We evaluate the different models that we trained on our training set. We evaluate their performance on the validation set. And the way that we could do that is that we take two combinations of whatever. So let's say that, for example, we have K, and we have a list that goes from K is 1 all the way to K is, I don't know, 50. So we have 50 options right here. And then we have another parameter setting, which could be, for example, the cleaning process that we do. So for cleaning, we have, say, lower casing, yes or no. We could have punctuation removal, yes or no. We could, for example, remove infrequent words. So infrequent word removal, yes or no. And we could even split this up in 3 different hyperparameters. So this could be 1, this could be 1, and this could be 1, right? So then we check the combination of all of these. So they could all be on or all be off, but just for the sake of this example, so that it matches this part, I just wrote them in a flat way of testing this. So we just do these individually, but we do test them in combination with all the K settings. So you can imagine that our unimportant parameter here is the cleaning process, which could be any of these values. And then K is this part right here, so that is our more important parameter. And this is grid search, this particular part right here. We make this grid of all our combinations, right? Sequentially, essentially. So K ranges from 1 to 50 in steps of 1. And this has these steps right here. So this is grid search. Now we can also do random search, which especially for these parameters that have these types of ranges, which we might not want to investigate all values of, right? There's always some importance point somewhere. So with random search, what we do is we just take a random sample off of these parameter settings. So we don't do this stepwise, we just take multiple ones in random intervals. And the intuition behind this is that we have more chance of finding the good parameter settings because we test more random intervals. So the chances that we hit a particular performance hill is higher. There's an associated paper that you can read if you find this interesting, which is Bergstrom and Bengio right here. They show that this random search is faster and it generally yields better models. So usually random search is preferred. Grid search is more frequently used though, and that's because not always are these hyperparameters all a range. Usually they're quite discrete, especially for data mining, kind of like the vanilla classic algorithms. Neural networks have a ton of these hyperparameter settings that are all these kind of ranges that can go from 0.1 until, you know, like floating points, all the way up until 0.999. So it's very difficult to come up with a sensible grid. So in that sense, random search would be better. But K, you know, usually you don't need up until 1,000. Usually up until 10 or something is more than enough to test. So then this random search doesn't really make sense if you have 2 discrete hyperparameters that you want to tune. Anyway, it's good to know it exists. So I'm just going to go into tiny slide mode here because otherwise this part falls off the page. This generally just illustrates the stratification. So as you can see, there are these data distributions over our labels. and we want to mimic that exact same distribution of the setosas, for example, here. We want to mimic that here and here. So I just want to draw the distinction here that stratification only pertains to the labels. So we only sample based on the label values. We could also sample based on the feature values. That is a different type of sampling. You'd really have to go into the distribution and do a very nuanced, maybe some type of Bayesian sampling. We're not going to go into that. Most basic thing that usually works is just doing label stratification. What people also do is when there's, for example, a minority class, or there's a very, very large majority class, and there's a bunch of different classes, let's say 10 others that are just less frequent. Doesn't have to be a binary problem. We could either oversample the minority classes or undersample the majority class. There are different algorithms for this. The most popular of which is SMOTE. I'm going to give you a very fast intuition of what SMOTE does. SMOTE knows the coordinates of the minority class and knows where all the majority ones are. And basically what it does is that it finds these in-between values of, could be, for example, the minority and the majority class, and then upsamples it with a minority instance that's synthetic. Could also be that we just generate more classes in between the minority one, more instances, sorry. But what we want to do is that we make the zone of which our minority class resides in a feature space a bit more dense, so that the some decision boundaries, for example, will be less tightly fit around this, right? So if these synthetic examples were here, we have a bit more of a fit right here. And in that way, give more room for generalization, in a sense. So this is SMOTE. So it just generates new instances based on the feature values of the known ones that are somewhere in between either minority instances or between the minority and the majority one. Now, what I would always recommend is that you just collect more data or look critically at your task if it's actually feasible with that little data. Over and under sampling they could prove very effective in terms of improving your performance for your particular sample. But you can imagine that it's pretty difficult to generalize using this. There's theoretical evidence that it does indeed perform better, but I think you should be very conservative with applying synthetic operations on your data. And I'm just going to state, just to be sure, that this is my opinion. So please feel free to test if whatever under or oversampling techniques you apply do work well. As I said, there's evidence for it, okay? But it does, to some extent, I would say, new data is always more reliable. Okay, so finally we go into evaluation. So we've talked about doing these this hyperparameter tuning, this bias, etc., generalization errors, and we have kind of dodged, we saw that we have these error scores, we have accuracy scores, but we kind of dodged what the more sophisticated evaluation scores are for these types of problems. Okay, so previously we covered R-squared, we covered mean squared error and root mean squared error. Then we didn't cover mean absolute error, but mean absolute error is essentially just mean squared error. So you can go back to the formulas that we discussed and basically you just drop the squared part. Now, mean absolute error is easier to interpret, right, as an error metric, because the error of mean absolute error corresponds exactly to the residual error. So you can see we're always this much off actually if we look at the label. And root mean squared error and mean squared error kind of obfuscate this, but they do correct for outliers in our predictions that would maybe blow up our absolute error too much because of these individual effects. So if you want to choose models, for example, so choose between hyperparameters, root mean squared error is usually better. If you want to report the final error, it's usually safer to interpret mean absolute error if you are reporting, for example. But do beware that you would probably have to look at some box plot or whatever over the absolute error so that you can see if there's outliers. Okay, so we're going to go into more advanced evaluations for classification. Now for classification, we generally like to look at confusion matrices. And confusion matrices put the prediction and the actual labels of the classes in this, this matrix. And then we say something about the relation between what the actual target was and what the predicted target was. Now you might know these from stats as, for example, type 1 and type 2 errors. If not, you can replace these parts right here with true and false can be correct or incorrect. So false positive would be a incorrectly predicted to be positive. Okay, and similarly you can translate these correctly predicted to be positive, correctly predicted to be negative, and incorrectly predicted to be negative. So a false positive would be, for example, telling someone that they have the flu while they, for example, have none of the symptoms, right? So that it might be that they don't actually have flu, but you diagnose them as having flu. A false negative is diagnosing someone who has the sniffles, is coughing a lot, and has a high temperature, that they don't have the flu, while they do actually have the flu, right? So you incorrectly say no, not the flu, and with the other one you say incorrectly yes, you do have the flu, while that person doesn't have the flu. Okay, so we abbreviate these by TP, TN, FP, and FN. Now there are several metrics that use these ratios. So we have accuracy, that's what we already saw. So that's the true positives plus the true negatives. So the ones that we correctly classified divided by the total amount of instances that we have. So true positive plus true negative plus false positive plus false negative. Then we get the correct percentage, right? If we would switch these to false, then we would get the errors, right? Rather than the accuracy, so we get the inverse. So then we have precision and recall, and these will be a bit more nuanced than accuracy. So precision, for example, is how much of the things that we classified as being positive was actually correct. And then recall would be how much of the actual positive instances, so the ones that we know are positive, did we classify correctly. So this is a difference between y hat and y. Okay, so that's why it's true positive plus false positives. So false positives that we incorrectly classified as being positive, so y hat, and true positive plus false negatives, so that we incorrectly predicted to be negative while they were positive, actually, so y. Okay, and we can combine these two, so precision and recall. We can combine those into an F score, which is typically F1, where beta is set to 1, so 1 plus 1 squared, and then 1 product of P plus R here. P and R are precision and recall. So we combine these into a sort of harmonic mean, so an average of rates, right? It's between 0 and 1. And then there's some weighting here on precision. So we can offset it to balance how important we think that these are. Typically it's a trade-off between precision and recall. So the more, generally, the more of the positive class you predict correctly, also the more negative classes you also predict as being positive, and the other way around. If you predict more accurately all the negative instances, you generally miss a bunch of positive ones. And this is exactly what the F-score captures, is this balance. So typically, the F-score is preferred over the individual precision and recall, but precision and recall might give you some more nuanced insights. Now, this is an example for you to work out. So you can label these as true negatives, false positives, true positives, and false negatives. Then if you chuck these numbers into the formulas on the previous slide, you should get these numbers. And this is F1 score. Now, in the interest of time, and also because there's a more detailed worked out example in the practical, I'm just gonna go by this particular slide. Now I just wanted to show you the receiver operating characteristic score. So what the ROC score does is that it gives us some intuition about how well our classifier performs compared to random guessing, which is this line over here in the middle. And this point over here would be that our true positive rate is very high, which means we have perfect classification right here. Now the angle right here is how well our classifier performs, essentially. So it balances this true positive ratio and the false positive ratio into some kind of metric. Now the way that it does that is that it changes this threshold over here of our data. It goes over the instances, then notes the classifications. So if this was correctly positive, then it is associated with some true positive rate of the total amount of instances. We go down right here, and per classification being correct or incorrect, the amount of true positive rates, true positives that we have varies, and the amount of false positives that we have vary. And this is noted per point, essentially. So each point here is at that point in our test set how much the true positive versus the false positive rate is. And then we can also calculate the area under the curve, as this is called. So this will give us a sense of how curved this is towards perfect classification. So this is an even more complicated metric to essentially show the same thing as many of these other evaluation scores, but just in a more nuanced way. Now we can plot our models kind of in this ROC space, right? So we might have one here that might go like this. And then we might have a model here that goes like this. I guess that would be here. So it kind of captures the curve, right? So the closer it is to this point over here, given these trade-offs between our false positive and true positive rate, the closer it is to perfect classification, the higher the ROC score, and the more we should prefer that particular model. So it gives us a sense of how much is it close to perfect classification. Now, just to quickly round off this lecture, there are certain schemes for splitting our data, for using or applying these metrics for model selection. The one that we have looked at up until now is called holdout, which is that we have a particular split. So we have 3 splits that are just hard cutoffs, essentially, and these are percentage-wise. And that's it. So we just train on this, validate on that, and test on this one. Now that also means that we just get one performance score for this exact training set. Now what happens if we vary the training set in a way? What we could do, for example, is that we just switch up the training set for once. So let's say that we just, this is now our val, this is now our test, and this is our data, training set, sorry. And then this is obviously our whole data set. So notice that our training set is now different, right? It's a different set of instances. And that means that we have a, say that we have a validation score for this. So the test score we're not going to look at. We have a validation score for this, which is, say, for a set of parameters, the best one here was k is 3 with 90% accuracy. And then here, k is 3 at 80% accuracy. So based on this set, we would have said, okay, k is 3, right? But here we have a lower performance score, whereas k is 5 on this split performed 85% correct. And on this set, it actually performs 90% correct. Okay, so k is 5 is best for this split. So here we have a 5% difference between two versions of our split. And here we have 10% difference. So on average, k is 5 is actually better if we would have taken different splits, right? If our training set would have been a different set of instances of our entire data. Now this is called k-fold cross-validation. So we do this cross-validation by changing the train and test sets. And this is 2 different folds. So we vary it 2 times in 2 different ways. And you could imagine that we could also split it up in 10 different variations, which we will go into a bit more in detail in the next video. Leave one out would be the same, but then our validation set is always 1 instance. So we train on everything, -1, evaluate on that. Now you can imagine that every split requires a new tuning procedure, new fitting procedure as well, and therefore it takes a lot of time. So the more splits you take, the longer it's gonna take. So the less speed it's gonna have, but the more fairness it's gonna have. So it's gonna give a fairer evaluation of the individual effects of the hyperparameter settings, etc. So typically, k-fold cross-validation is a good trade-off between these. So we have some variance, but it also doesn't take us an incredible amount of time. Leave one out would be the most fair one, but it also takes a very long time, okay? And holdout is something that is generally preferred if you don't want to tune, for example, say that you only run logistic regression with 1 parameter setting, you can do holdout. Just drop the validation set and no problem. Or if your data is so big that you don't even need to, there's so much variance anyway in our validation set that we don't need this split. But generally, if you have reasonably sized data, k-fold cross-validation, even for very big data sets is generally still a good idea. So this was quite short. I will go into more detail about this in the next lecture. So see you there.